Hi everyone, welcome back to Everything is Relative with me, Mr. K. Today we'll be doing a crash course on the topic of magnetic fields for Cambridge A-Level Physics 9702. Now remember, our crash courses are just meant to cover at a very high level the concepts and the topics, the subtopics that will be important to understand for the exam. So it's not going in depth, but simply covering everything at a very high level. Now, magnetic fields is one of the longer topics, if not the longest topics in A-levels, in Cambridge A-levels at least. So for CAIE, there's a lot to know and a lot to understand, and it can get overwhelming. But that being said, if it is the longest topic with the most amount of concepts, it is highly possible that that could be a fair portion of your examination. So it's no good to leave out or omit the section when studying. So we'll try to break it down as simply as possible. It's a lot of stuff to cover, so we're going to move at a fast pace as well. But this, again, is just to bring you back up to speed with everything that you may have forgotten during the term. Now, what do we know about magnets? Now, without going into the detail of why this happens, you more than likely would have seen a magnet at some point. If it's in the school lab, you'll see one that looks similar to the bar magnets that I have here. They are color-coded. And they have a north and south pole. They always exist in two poles. And if I bring a north and a south pole close to each other, we know there's an attractive force. So these are called bar magnets, to be specific, because they are in the shape of a bar. And we have unlike poles near each other. And so what we realize is that unlike poles attract. And if I bring two north poles to each other, near to each other, or two south poles for that matter, any like poles, and the opposite will happen. There's still a force between them, but now it's a repulsive force. So we say like poles repel. Remember, this is not analogous to the force between charges, because that exists as a monopole. A charge can either be positive or negative. But a magnet must exist as a south and a north pole. There doesn't exist magnets of just a north or a south pole. So what we first need to discuss is the topic of field lines, more specifically magnetic field lines. Now you would remember from gravitational fields that we had gravitational field lines, and these basically tell us the same thing, or a similar thing. In essence, these are lines of magnetic force. So if we follow the lines of a magnetic field, we follow the lines of the force. And in this case, magnetic field lines tell us the direction of a free north pole, direction that a free north pole would move if it were placed in a magnetic field. So let's just copy and paste our magnet again. Just make it a little larger. Now, there are forces that will be exerted on another magnet if it were to come close to this magnet. But we need to visualize these forces. So the field lines are imaginary, they're for us, but it gives us an idea of how the field can be drawn. So I'll just rotate it so that my north pole is on the left, doesn't really matter. And if I were to draw field lines, I notice that the field lines start on the north pole and terminate on the south pole. And so even for just a single magnet, I have the start of a field line and the end of a field line. Again, excuse my drawing. But as we go further from the magnet, then the field lines are not as tightly packed onto the magnet. And you can see we start on the north, end on the south of the very same magnet. And if you did this experiment with iron filings, you would have seen this pattern emerging, obviously without the arrows, but you would have seen a very similar pattern emerging with iron filings if you place this magnet under a piece of paper, plain white piece of paper, and you scatter the iron filings over the piece of paper, and you notice that these patterns emerge. That's because the iron filings, which are magnetized themselves, will follow the lines of force, follow the magnetic field lines. And so we get these field lines that have a nice symmetric pattern to them. And so this is for a single bar magnet. So field lines start in the north, end on the south. And so what happens if I bring opposing poles, or the poles of two different magnets together? So let's first do this for, again, we can make these quite large, just so that it's easier to observe. So if I bring a north pole of one magnet close to the south pole of another magnet, what happens is the field lines do exactly the same thing. They point from north to south, and unless the surfaces are completely parallel or completely parallel to each other, then the field lines will curve and arc out a bit. Okay, so they're not all straight lines, so the field is not always uniform. It's not uniform between two magnets. And so again, you would see a very similar pattern if you now replace a single bar magnet under your piece of paper with two bar magnets. Starts on the north, ends on the south. That you wouldn't be able to observe, but the pattern, the shape of the lines will look very much the same. And then if I now bring like poles together, notice how the field lines all join the two magnets. They go from one magnet to the next. So if I were to throw in, if I could, for example, find a free north pole, if that could exist, and I drop the north pole here, the north pole will be repelled from the north pole of the first magnet and attracted to the south of the second. And it'll follow the path along the field lines if there was such a thing as a free north pole. Now, if I change the scenario just slightly, if I simply take the magnets and now bring the north poles next to each other, then the field lines look very different. Again, this can be easily achieved with the iron filings. So now they exit from north poles and they are repelled by the opposing north pole. And so basically what happens is that they move away from each other. They leave a nice big empty space in the region between the magnets. The space in the center is a space where there's little to no force. There is a repulsion and these two magnets will repel each other, but there is a neutral point somewhere in between. So if I placed a free north pole right at the center, it would experience no force. The force from the right-hand magnet will balance the repulsive force from the left-hand magnet, and it will just remain stationary. And so it's clearly different when we have like poles and unlike poles near each other. So some of the rules of field lines, again, this will be in your textbook, you need to read and understand, but the reason why we use field lines is simply so we can have an idea of a visualization of what the force would look like. If I throw a north pole in there, where would it move? Similar to the field lines for electric charges. If I throw a positive charge in the field lines, where would the positive charge move? And so what we know about field lines is that they start at the north pole. I'm going to write this in shorthand. Obviously for you in a question, you'd have to write this in a full sentence or as a full sentence. Start at the north pole, terminate at the south pole. We also know that field lines never cross. Why do field lines never cross? Because that would be ambiguous. We cannot have 2 points anywhere in space would have 2 forces coming from the same object. Okay, there should be one force and only one force. And so if the field lines cross, that would be ambiguous. It's non-physical. They also, I'm going to write this in short form, give the direction, like I said, of a free north pole or an isolated north pole. That's the direction a free north pole would move if it was thrown into the field. If there was such a thing as just a free north pole, which there isn't. And the last thing that field lines do is indicate the strength of the field, how strong the field is. So I didn't make this very clear in the diagram, but the field strength is indicated by the closeness of the lines. So what you would notice is as we get further from the magnet, the field lines are, consecutive field lines are further apart. And what this means is that the field is weaker further from the magnet, which sort of makes sense. As you get further from the magnet, the magnetic field strength is weaker. If you pull these magnets very far apart, you'll notice the iron filings don't have much of a well-defined shape anymore. And so that's why the distance between consecutive field lines will tell us the strength of the field. So as you get further from the magnets, the field gets weaker. The magnetic field gets weaker. So closer field lines means a stronger field. And so if I wanted to define a magnetic field, it's not that easy to define a magnetic field, but we'll try. Now, we have to be very careful that we don't confuse a magnetic field and an electric field. There's something very important that distinguishes a magnetic field from an electric field. Now, a magnetic field is a region of space, like any field, is a region of space where something feels a force. Now, that something is very important because this will make or break the definition. Where a moving charge, a moving charged particle, or permanent magnetic pole experiences a force. Why can't I say just charge? Why can't I simply say charged particle? Okay, why do I have to say moving charge? Well, that's purely because by saying a charged particle, we could also be including stationary charged particles. If a stationary charged particle is feeling a force, it's not necessarily feeling a magnetic force, it could be feeling the electric force. So only moving charged particles, like we'll see later on, only moving charged particles feel a magnetic force. Stationary charged particles will not feel the magnetic force. So we'll see that later on. But magnetic poles will always feel a force in a magnetic field. Okay, so a permanent magnet will always feel a force in a magnetic field. So the first thing we want to discuss about some of the usefulness or the uses of the magnetic field is the motor effect. It's called the motor effect because, well, it's the effect that allows motors to operate. What is the motor effect? Well, simply, we'll bring back our magnets. So let's say I have the north pole of one magnet facing the south pole of another magnet. Now, since the north face and the south face are parallel to each other, at least at very close distances, we notice that the field lines will be uniform. We have a uniform field in the region between the faces of bar magnets. Now, if I place a wire in that field, so this is a copper wire, and if I place this wire in the field, what I notice is that nothing happens. Wow, that's great. All this drawing for nothing to happen. Field still continues to go, but there's no current in this wire. It's just a neutral wire, and nothing happens to the wire. But I'm going to change this scenario very slightly. I'm going to leave the magnets as they are. Okay, north to south, and so the field lines point from north to south. I'm going to redraw this diagram with one small change, and that is that current is now flowing in this wire. So now I have a current in the wire, and we notice something strange beginning to happen. The wire feels a force. This is, in very simple terms, the motor effect. There is a force on the wire. So when current flows, specifically when current flows at some angle to magnetic field lines, then the wire in which the current is flowing feels a force. Or we sometimes say the current is feeling the force. And so that's quite an important concept to understand, that only when the current flows will a wire feel a force. If I remove the current, then there isn't a force. Now, remember, this force will make the wire move either to the left or to the right. It will be repulsive or attractive, or move in or out of the page, something. It's a force. So what's important about a force always is two things. Since it's a vector, we need its direction and we need its magnitude. And normally we usually go straight to the magnitude first and then figure out the direction later. Since we aren't studying vectors in this course, we're going to have to use a trick. Well, I wouldn't call it a trick. We have to use a little piece of imagination to find the direction of this force, and we use something called Fleming's left-hand rule, which looks something like this. So if I take my left hand and I curl my fingers in such a way, if I extend my fingers outward in such a way that my thumb, my index finger, so my thumb, my index finger, and my middle finger are all at right angles to each other. So you notice F and B are at right angles, F and I are at right angles, and I and B are at right angles. So I essentially create a right-handed system where all three fingers are at 90 degrees to each other. What I have is an idea of how to use Fleming's left-hand rule. So if I can position my hand in such a way so as to match the diagram that I'm looking at, in which I want to find the force, the magnetic field, or the current, then I use the left-hand rule. The thumb gives the direction of the force. So F here is the magnetic force that is felt by the wire as the current is moving. B, we haven't defined B just yet, but just think of B. You've already studied this topic, so you know that we use the symbol B for the magnetic field. Remember, the magnetic field is pointing in a straight line. We're only considering uniform fields. A uniform field always points in the same line, and so it's pointing in a straight line along the index finger. And the middle finger gives us the direction of the current. So I have to match the direction of the current with what I have in the diagram. If I were to look at this diagram, I'm going to take this diagram and I'm going to bring it up here next to the magnet at the bottom. So what I'm going to try to do, actually I can't do it with this diagram, but what I would do is I would take my middle finger and point it upward. Just be wary of the surroundings when doing so. I will notice that my field is pointing from left to right. B is pointing from north to south, left to right. So in that scenario, I have B pointing from left to right, my middle finger pointing upward, and so my thumb naturally will point into the page. And so what does this mean? This means that the force on the wire is into the page. Remember, these three are all perpendicular to each other, so something's going to be going in or coming out of the page. It turns out in this case, the wire will be pushed into the page. If I reverse the current and I use the left-hand rule again, then the force on the wire will be out of the page. Okay, so that's how we use Fleming's left-hand rule. And so if I were to draw this as a three-dimensional or right-handed system, then what I'd have is that my force field and current are all at 90 degrees to each other. And so yes, you could use vector methods to work this out, but that would be a lot more complicated unless you are very, very confident that you can do the necessary vector calculation. So we use the left-hand rule to avoid using unnecessary vectors. Now that we have the direction of the force, we need to find the magnitude of the force, the size of the force. So the size of the force also can be fairly difficult if you're not using calculus and vectors. But if I had a wire carrying a current I at some angle to the field lines. Now we're not going to assume that the current and the field are at right angles. Okay. So it's possible that the current and the field are not at right angles. It could be that the current is at some angle to the field. Then the left-hand rule becomes a little bit more difficult to use. So if I have the field B, again we give magnetic field strength or magnetic flux density to give it its real name, its true name, symbol B. The angle between the two is theta, and the length of this wire, at least the length of the wire in the field, is L. The amount of wire in the field we call L. Now, what we have is that the force on this wire is proportional to IL sine theta. Okay, but what we actually want is the perpendicular component of the force, which is, actually we can convert this, let's first convert this into an equation. We get F is equal to, remember, if we're going from something that's a proportionality to an equation, we have to add a constant of proportionality. In this case, the constant is B. So F is BIL sine theta, where B here is the magnetic flux density. We'll come across the word flux a little later on, but the actual name for B is magnetic flux density. And if I rearrange the equation above, I can get B is equal to F divided by IL sine theta. Now, why do we use sine theta? It's simply the component of the force that is perpendicular to the current, or the component of the field that is perpendicular to the current. It gives us the maximum amount of force. If the current at any point becomes parallel to the field, the force becomes zero, because theta becomes zero. So if theta is 0 or 180 degrees, sine theta is 0, there's no force. So the current, the wire must be at some angle to the field lines in order to feel a force. If I want the force to be a maximum, sine theta must be 1, which means theta must be 90 degrees. And so when theta is 90 degrees, when the current and field are perpendicular, then the force simply becomes F is equal to BIL. So the sine theta will disappear if theta is 90 degrees. Okay, so if we have this expression for B, this is where the definition for magnetic flux density comes from. If they ask you to define magnetic flux density, it's one of the more difficult definitions. Simply look at this equation. B is F over IL sine theta. It is the force per unit current per unit length. Oh, but the sine theta is a bit annoying. So let's write it as F over IL if theta is equal to 90 degrees. Okay, this makes it a bit easier to do the definition. So the magnetic flux density B is the force per unit current per unit length on a current carrying conductor that is perpendicular to the magnetic field. Okay, so it is a force per unit current per unit length on a current carrying wire, on a straight current carrying wire placed perpendicular to the field. There we go. The definition arises from this equation. And so if theta is equal to 90 degrees, F is simply bull. F is bull when theta is 90 degrees. And B is equal to full, F divided by IL. And so from here we can see that the unit of flux density is Newton per meter per ampere. Okay, but we give this another unit to make sure that our laziness is intact, and we call this unit the Tesla. Uppercase T for Tesla, named after Nikola Tesla. And so the unit of measurement for magnetic flux density is the Tesla. Okay, now that we have the mathematics out of the way, we can talk about the force on a moving charge. Now, why did we suddenly go from a wire to a moving charge? Well, it's simple. It's not purely the case that the wire is feeling the force due to its inherent properties. It's the fact that a current is made up of moving charges that the wire feels a force. And so if I isolate a single charge Q, any charge particle, an ion, an electron, a proton, whatever it may be, and I place this at some angle to a magnetic field, think of what I was doing earlier, but now instead of an entire wire of current, I only have a single charge. It's moving with a speed v, which in many cases will be the drift velocity of any wire. Again, let's not assume that, let's just assume it's moving freely in a magnetic field, which will define a magnetic field that has a flux density of B, and theta is the angle between B and V. And what happens is the force on this charge particle, and we aren't going to derive it, but it should be in your textbook and you should know how. F is B Q V sine theta. And this gives us the magnitude of the force that a charged particle feels when it moves through a magnetic field. Now this is why in the definition of magnetic field I said that it has to be a moving particle, because the force depends on the velocity. If it's not moving, if this charge was stationary, guess what? The force is zero as well. There's no magnetic force on a stationary particle, on a stationary charge particle. And if I wanted to find the direction, I have to use Fleming's left-hand rule. Now, I want to make it very clear that, as I didn't point this out earlier, Fleming's left-hand rule gives the direction of current. When I say current, I mean conventional current. I mean the flow of positive charge. So if this were the case of electrons, you would flip the direction of your middle finger. Okay, conventional current is the flow of positive charge. If you were electrons flowing, you would flip your hand so that your middle finger points in the opposite direction. A conventional current flows in the opposite direction to negative charge. Okay, so that is how we find the force on a moving charge. Now it turns out that also something very, I wouldn't say peculiar, but something a little bit odd happens when we move a charge into the region of a magnetic field. So looking at this picture, we have a very weird diagram. What this means, if you see a circle with a dot like that, is that the field is out of the page. If the field were into the page, we'd use a circle with an X. We'll look at another example that has something like that later on. But a circle with the dot in the center means the field is pointing into the page. Since I can't use an arrow because of I'm using a two-dimensional plane. I can't see the arrow, and so I use a dot to say that it's going into the page. Then I have a charge on its merry way, has a charge q and a mass m, and moves into the magnetic field. Now I use Fleming's left-hand rule. It's a positive charge, moves into the field which is pointing out of the page, and what happens is it'll feel the force. But it turns out that the force it feels is always at right angles. It's always at right angles to the charge. And so what happens is, at every point, there is a centripetal force acting on the charged particle. And because of this, it moves along the arc of a circle. And it continues to move in a circular arc as long as it is in the field. If you notice this diagram, if the field were large enough, it would just move in a circle. That's the basis behind the principle of your magnetron, your cyclotron inside your microwave oven, for example. We can spin charges in a circle if we have a magnetic field large enough. But if it were to go in and then leave, it enters by moving in a straight line. There's no other forces acting on it. The force acts at right angles. The magnetic force acts at right angles throughout its time inside the field, and then when it leaves the field again, it continues to move in a straight line. But as long as it stays in the field, the force on it, the magnetic force on it, is BQV. Theta is 90 degrees because the velocity and the field are always at 90 degrees to each other, since the field is pointing out of the page and the velocity is along the plane of the page. But this, from our knowledge of circular motion, is mv squared over r, where r is the, so if this was a circle, there'd be a radius from the center of the circle to the center, to the point on the circle, and that radius is r, and so that's equal to mv squared over r. That means the radius of the circular path, if I do a little bit of mathematics here, is mv over the flux density B times the charge Q. Now, what I know is that the mass to charge ratio, m over q, is actually constant for all charged particles, and it's unique for all charged particles. Every single charged particle, whether it's an ion or a proton or electron, has a unique value of m over q. That's very important because I can use the size of a radius of the arc of a charged particle to find its velocity, or to even find the field strength B. And so this is a pretty neat method of determining, if I also can determine what the velocity and the flux density are. If I know what the velocity and the flux density are, I can find out m over q using this expression. And so I can identify what type of particle, what type of charged particle is going into a magnetic field. Very interesting application. It's used in spectroscopy to determine what type of particle we are looking at, what type of gas we are looking at. If we ionize a gas and get it to move in a circular arc inside a magnetic field, the radius of its circular motion tells us exactly what particle we're looking at. Okay, the next thing, I know we're moving at a quick pace, but there's a lot to cover, is velocity selection. Now, like the name suggests, it simply means we need to select a velocity. So, we won't talk about the applications too much, but imagine that we have a scenario where I'm going to cross fields now. I'm going to have an electric field. You remember your topics of electric fields and capacitance. A uniform electric field points from positive to negative. And so the electric field points downward. And we also have a magnetic field which looks as follows. So let's assume we have our electric field pointing downward, our magnetic field, and now we get to use the crosses. So the circles with crosses means that the magnetic field points into the plane of the paper, into the page, and I have positively charged particles moving into this region of the field. Now, if positively charged particles move into the field, then what I know is that the electric field will pull these particles downward. What I also know is that the magnetic field will do the opposite. The magnetic field will pull these charged particles upward, since the magnetic force will be upward if we use Fleming's left-hand rule. And so if I want particles to move straight through, undeflected, and let's assume I put something to capture these extra charged particles. If I want these charged particles to move straight through and be undeflected, remember I have a force FB pulling it up, and I also have force Fe pulling particles down. So now it turns out that if I want the particles to move undeflected, then the forces must balance. The upward force must balance the downward force. So Fe must balance Fb. And this is Q times E from our topic of electric fields. This is equal to QVB. The Q's cancel. I'm left with V equal to E over B. So any particles that enter with a speed of E over B will exit without being deflected. V is equal to E over B. If V is greater than E over B, what does this mean? It simply means QVB must be greater than QE. Charge is the same. Okay, so they will be deflected upward. The magnetic field is stronger the faster particles move. The electric force doesn't really care about its speed, and so if the speed is really slow, the electric force takes over and pulls the charged particles downward. And so V is less than E over B, and this comes from the fact that QVB is less than QE. So I can select particles. Let's say I only wanted particles of a certain speed. I can apply this velocity selection to absorb particles, to remove particles that don't have a speed of E over B. Why? Because if I set the values for E and B, I can choose exactly the speed V of particles that I want. Maybe I have an experiment that purely needs a certain speed of particles, and I can restrict the speed of particles by doing this. Okay, so I keep this gap small enough so that only particles with a speed V is equal to E over B can pass straight through. Okay, so if I were to draw the charge, a free body diagram, or force diagram, the left-hand rule tells us that the magnetic force is up, and our knowledge of electric fields tells us that the electric force is down. And so we can balance these two forces so that the particle continues to move from left to right. Okay, so that's a little bit different. That's the topic of velocity selection. It's not too difficult. But the next one is a little bit more tricky. Okay, and this is the topic of the Hall effect. Now I know many of you want to omit this from your studying, leave this out. I wouldn't suggest this because when you take the time to understand it, you realize that it's not that bad. Okay, so let's draw a diagram to see what this looks like. So I'm going to consider some conducting material. I'm going to take a slab of some conducting material. It doesn't really matter what kind of conducting material this is. So this is a slab of a conductor. I'm going to draw a small cross section of it, like I have done here. I'm going to apply a magnetic field downward. I'm going to use something that will generate a magnetic field downward onto this slab of material. And so I'm going to call this magnetic field, I'm going to give this magnetic field a flux density B. And at the same time, so let's also label parts of this conductor. This conductor has a thickness T, lowercase t. And what I'm going to do is I'm going to pass a current through this conductor perpendicular to the face at the bottom, perpendicular to face, let's call it A, B, C, D. Okay, again, this is a common past exam question. In the absence of a magnetic field, what would happen is the current would pass straight through the conductor. It would be undeflected. It would pass straight through the conductor. And so let's just give this current a name as well. We'll call the current I, as we usually do. Now, what happens in this case is we have a magnetic field. Now, again, this is, and we're also going to assume that this is electrons. Because we said Fleming's left-hand rule works for conventional current, but this is a physical situation. It's a physical thing that we can observe, and so we'll stick to the physical idea, which is electrons flow, and they flow through this conducting material nice and freely. And what happens is that these electrons flow undeflected if there's no magnetic field. But using Fleming's left-hand rule, you have to be careful about the direction of your middle finger. The middle finger does not point into A, B, C, D, but now points out of A, B, C, D, simply because it's negative. These are negative particles moving in. Your index finger points downward because that's the direction of the magnetic field, and your thumb, which is the force, points to the right. And so the force acts on the electrons to the right. So what happens is these electrons curve off and begin to pile up on the left-hand face. And so what we get is electrons on the left-hand face. So the left-hand face, we can call it BD, we give it random names, BDLM. Electrons gather on the face, BLDM. Aha, so that makes the face negatively charged because I have electrons all piling themselves up on the left-hand face, and then positive charge as a result of the overwhelming number of negative charges lining themselves up on the right-hand face. Positive charge is induced on the opposite face. We won't have to give the opposite face a name, but the face opposite, the side opposite, the negative charge obviously becomes positively charged. And so what do we remember? If we remember from the topic of capacitance, if I have two lines of charge, one positive and one negative, I generate a potential difference and an electric field E. So there's a potential difference V between the two faces. And so what we call this is we call it VH. So it's named after the person who discovered it, Hall. And so we call it a Hall voltage. It is simply a potential difference that exists between the faces. Oh, okay. So what does this mean? Now electrons can't move to the negative face anymore. There's an overwhelming amount of negative charge. It repels them. They move with the field lines, against the field lines rather, since they are negatively charged, and they begin to move towards the positive face. So they feel a force that will pull them to the left. So they were initially moving to the right, but they will feel a force that starts to pull them more to the left. But we aren't going to go that far. It's going to decrease the amount by which they are deflected until eventually they just move along the blue line. So what we have is that the electrons will be pulled toward the positive face, which is the opposite face. And at some point, the electric field, the electric force will equal the magnetic force, the electric force pulling to the left balances the magnetic force pulling the electrons to the right, and guess what? The electrons are undeflected. Now you're probably thinking, why go through all this trouble to just let the electrons flow straight through anyway? And the reason why is because, and again I'm not going to derive this, but it's a very important equation. VH is actually, if I connected a voltmeter across the two faces and I measured the value for the potential difference, I get VH, the Hall voltage. The Hall voltage tells me that VH is B times I, the flux density times the current, over little n, which is the number density of charge carriers that depends on the material that you're using, times the thickness of the material, times the charge, which is in this case is the charge of an electron. This is called the Hall voltage. So the Hall voltage is set up once the force, the electric force, is equal to the magnetic force. Now the reason why we go through all this trouble is, so if you look at this equation, if I connect a voltmeter and I find VH, if I know the current I, the number density of charge carriers I know if I know the material. For every material that's unknown. The thickness is also known and the charge of the electron is also known. What that means is I can use that to find the flux density. It is the most used method of finding the magnetic field for an unknown field. If I want to find the strength of a field, I use a Hall probe. A Hall probe uses a thin slice of metal, rather a thin slice of semiconductor, to find the Hall voltage, or rather use the Hall voltage to determine the flux density. So Hall probes have a known value for I, N, T, Q, and with the value of VH that is found when you place a Hall probe into a magnetic field, B is then determined. That's why we go through all of this trouble, to find the Hall voltage. So you see, it's not that difficult. It does require reading, but if you read it a few times, if you maybe pause this video, rewind it, slow it down, it's not that bad. And especially if the question gives you the diagram and says, hey, tell us which face the electrons move to. Tell us which face the positive charge is located on, etc. It's not impossible to understand. Now the next thing we have to talk about is the magnetic field of a current. Now we spoke about what happens to the force on a current. What about, where does this force come from? Why does it exist? And that's because a current carrying wire, I'm just going to draw it as a straight line. So this is a straight current. Okay, it's a current moving in a straight line, so I'm simply going to call it a straight current. What we notice is that if this is vertically upward, and again my poor drawing skills are being showcased here, what I get is that the magnetic field is a loop pattern. It's circular. So for a straight current, I get a looped or circular magnetic field pattern. And the other way is also, again, just picture this in your mind as a loop of wire. Okay, now it doesn't look like that, but this is a loop of wire. So this loop of wire means that current flows in a circular path. The current flows in a loop. Well, guess what? To maintain the symmetry, we call this a solenoid or a solenoid. What happens is that as the current flows, and we can assume the current is flowing in any direction, we have the field lines, a magnetic field being generated by the current, and this field is uniform inside the loop. So inside a loop of wire, the field lines are uniform. And so we'll just write this as, instead of straight field lines, we'll write uniform magnetic field. So anywhere inside the loop, the flux density is constant and the flux density direction does not change. It's always left to right in this case. And so that's an interesting thing, and that's why wires feel a force when placed near a magnetic field, because they also produce their own magnetic field. And only the two fields can interact, and that's why there's a force of attraction or repulsion. And so a straight current produces a looped magnetic field, a looped current produces a straight or uniform magnetic field. Okay. If I had a flat coil, it's one of those in your textbook. So if I were to draw simply one loop, instead of multiple loops of a coil, I draw a single loop. And so current is moving from bottom to top. Then I get the field lines moving circularly around the loop, moving in a circle around the loop. And they stretch out at different points. At the center of the loop, right through the center, it'll appear as a straight line, but at other points it'll be stretched out in a circular shape. And so we can use the right-hand grip rule. We won't explain the right-hand grip rule, but that's, since it's a lot simpler, but the right-hand grip rule can be used to find, basically if you grip all the fingers of your right hand and you extend your thumb as if you were showing thumbs up, the curl of your fingers gives you the direction. Well, if you're thinking about a current, then your thumb gives you the direction of the current and the curl of your fingers gives you the direction of the magnetic field. And vice versa, if you were looking at a solenoid, the curl of your fingers gives you the direction of the current and your thumb tells you in which direction the magnetic field is. And so this is for a flat loop, and in purple we have the field lines. Okay, what's also important to remember here, and I'm not going to go into this in detail, is that if I take two long straight current carrying wires, they feel a force. Okay, and so if I were to draw the field lines, again I would use the right-hand grip rule to find the direction. And so that's the field of the first wire. Let's assume the current is flowing upward in both wires. Then we'd have the field looping in that direction. And for the second wire, we'd also have the current looping in a similar direction. And so at the point at which they meet, we can see that the force on the wire to the left is pointing inward, pointing to the right, and the force for the wire on the right is pointing to the left. And so we can use the left-hand rule to find that. And so what we notice is that like currents, not like charges, not like poles, but like currents will attract each other. So if you put two wires next to each other that have currents pointing in the same direction, you have to be very careful. The wires can short if they come too close to each other. And then in the opposite direction, if I have currents moving in the opposite direction, then the force is a repulsive one. And so if one of the currents is flowing upward and the other is flowing downward, then I have a repulsive force. So this is the opposite of thinking of electric charges or poles. Unlike currents repel, and like currents attract. Piece of extra information, because a question could rely on your ability to understand that principle. Okay. Now the next part also is fairly confusing, or can get fairly confusing. This topic really doesn't let up. Electromagnetic induction, specifically Faraday's law, but also the idea behind it. So I'm first going to define something called the magnetic flux. We spoke of the magnetic flux density, We haven't spoke about the word flux. Now flux, at least in physics, is simply the amount of something passing through something else, passing through a region or an area. And we give it this Greek symbol phi, the Greek letter phi, which is the flux density B multiplied by the area. What does this mean? That means if I have a region, maybe a plane, and the plane has an area, a surface area A, and I have the field lines pointing from some uniform magnetic field, we'll consider it all uniform for now, at an angle theta to the area or the normal vector for the page. The angle theta means that the flux phi is B times A times the sine of theta. Now we are only going to assume the case in which B and A are perpendicular, and so phi is simply BA, sine theta is 1 because theta equals to 90 degrees. You're going to assume they're always perpendicular, just for the ease of understanding. The units of measurement, I use square brackets usually for units of measurement, is Tesla meter squared, and again we give it another derived unit which we call the Weber, which is an uppercase W and a lowercase b. So be very careful about using symbols as units of measurement. Now, why did I mention the magnetic flux? Because I want to mention another quantity. Now, there's a lot of quantities here, a lot to remember, but bear with me. It's something called the flux linkage. It is N times phi, and this is B times A times N, ban. Okay, and again we're assuming B and A are perpendicular. That's where the sine theta disappears. Okay, so what is this basically? Well, think of it this way. If I have a flat loop of a coil, then the surface area of this coil is A. The field passes straight through the center of this coil, B, at its center, and so the flux passing through the one face, phi, is B times A. Flux linkage is, instead of having a solenoid with one loop, which is not usually the case, I usually have multiple loops of coil. If I have multiple loops of coil, then each of these has an area A. And so the magnetic flux phi is BA plus BA plus, well, it's the sum of BA for the number of coils that I have. If I have n loops of coil in the solenoid, then phi is simply BAN. That's basically what I'm talking about. N is to tell me the number of loops I have in the coil, simply. Why is that? Because I need to describe Faraday's law of electromagnetic induction. Now, basically, what does this say? Now, I know, again, these are things that you may ignore when studying, because it might be a bit overwhelming. But simply, Faraday's law of electromagnetic induction says one important thing. A changing magnetic field induces an EMF in a conductor. Very important point. Magnetic fields induce current. Magnetic fields induce EMFs. And so a changing, meaning the magnetic field is constantly changing, this induces an EMF in a conductor. And so mathematically, Faraday's law says that the EMF induced in a conductor, when I place a magnetic field that's changing, that's moving, next to a conducting piece of wire, the wire suddenly gets a magical current in it. Not so magical, because mathematically this is the change, delta, in the flux linkage, which we already defined, n phi, divided by the change in time, is the EMF produced. So simply says the change, Now it has to be a change in flux linkage in order for the EMF to exist. So a change in flux linkage divided by a change in time gives me an EMF. So the rate of change of magnetic flux linkage with a minus sign gives me the EMF produced in a conducting wire. Now this minus sign comes from something known as Lenz's law. Now you would have seen this as well, and again it may have just frightened you a bit. What is Lenz's law? So basically Lenz's law says the direction of the induced EMF is such as to oppose the change that is producing it. Yes, you may have memorized this definition, as you should. The direction of the induced EMF acts in a way to oppose the change producing it. What does this mean? Let's assume I have a wire with a current placed next to a wire with no current. Faraday's law says that the current, or the EMF, induces, or the motor effect rather, says that this current induces a field. We know that a current, a moving charge, induces a magnetic field. And so I have a nice circular magnetic field being produced around, in a circular loop around this wire. Let's connect this wire to a power source. So we know its power is not coming from anywhere. Power source, resistor. So we give power to this wire. I place a second wire next to the first. I bring it close to the first wire. Magic happens. Faraday's law says a change in magnetic field. If I can change the current in the first conductor and change the magnetic field or the flux density, I induce a current or an EMF in the second wire. Now notice that one points up and the other points down. That's what Lenz's law is telling us. It says that the field of the first wire induces a current, or actually an EMF to be more technically correct. The EMF will eventually induce a current that opposes the original. That's where the minus sign comes from in Faraday's law. So this current that's induced will always be in the opposite direction as to the first. And that's where the minus sign comes from. This is to allow for the conservation of energy to stand. You can imagine that if we have a current in one direction generating a current in the same direction generating a current, this would be an effect that would just stack up. And so energy would not be conserved. And so this happens so as to cancel out the effect so that energy is conserved. That's all that Lenz's law says. And so if you think about the application of Lenz's law, looking at some past exam questions, it's actually now not that difficult. Any EMF that is induced, or any field that is induced, will oppose the original EMF or the original field that caused it. And how did it cause it? It caused it by Faraday's law of electromagnetic induction. So I know this was fairly rushed, and yes, this is a long topic, so it does require a lot of time and effort. But I'm hoping that some of the concepts that I explained here just made the topic a little bit easier, that much easier to understand. Like I said, it is a very long topic with a lot of concepts. But I tried to break them down as simply as I could to help you in answering questions. So until next time, I'm Mr. K. We'll see you soon on Everything is Relative.